All right, let's dive into some chemistry simulations today.
Sounds good.
We're tackling acid-base titrations, but not the way you usually think of them.
Yeah.
We're looking at a JavaScript model for these.
Oh, cool.
You know, I think this is going to be really interesting because this simulation gives us so much control.
Yeah, it really does.
And it lets us visualize things that would be tough in a real lab.
Mm-hmm.
Now, you've probably done some titrations in the past, so we're
Yeah.
not starting from scratch here. But let's imagine we're in a virtual lab.
Okay.
And we have this acid solution, and we don't know the concentration of it.
Right.
We're going to use this JavaScript model to figure that out.
Awesome.
So it's called the ACE Acid Strong Base Titrations JavaScript model,
Okay.
developed by Fernando Silva Fernandez.
Mm-hmm.
And it's built using something called easy Java simulations.
Oh.
I know you're probably wondering what our first move is.
Yeah, where do we go from here?
Well, we need a base solution
Okay.
with a known concentration.
Right.
But here's where the simulation gets really cool.
Yeah.
We can actually tweak the parameters,
Okay.
like the volume of acid,
Right.
the concentrations of the acid in the base,
Mm-hmm.
even this thing called the acid ionization constant, or Ka.
I see.
Ka.
Chi.
Rings a bell, but I'm not sure I remember exactly what it is.
Oh, well, so chi, think of that as like a measure of the acid strength.
Okay.
So it tells us how easy it is for that acid to give up a proton
Okay.
or a hydrogen ion in solution.
Mm-hmm.
So the higher the Ka, the stronger the acid.
Okay, yeah.
And that'll affect the pH as we add the base.
Okay, so the simulation's doing some serious number crunching behind the scenes.
Yeah.
It's not just like a simple visual tool.
Right.
It's got some real power under the hood.
It does.
So we can actually watch the pH change as we add the base.
Okay.
All beautifully graphed out for us.
Cool.
But there's something even more important than that. It's the equivalence point.
Right. The equivalence point. That's the big moment in any titration. Mm-hmm. So how does the simulation show us that?
Well, it actually shows it in two ways.
Okay.
It shows it visually with, an indicator changing colors, and it does it mathematically by calculating the point where those moles of acid and base are equal.
Okay. And it uses that titration coordinate.
Right, the titration coordinate F.
What exactly is that?
Well, so F is just the ratio of moles of base to the moles of acid we started with.
Okay.
And at the equivalence point, F equals 1.
Okay.
So that means we've added just the right amount of base.
I see. So the simulation's really doing a lot of work behind the scenes.
Yeah, it really is.
It's calculating all these different things.
Yes.
And it's giving us this nice visual representation.
Absolutely.
But you know what? I think there's more to this, isn't there?
Yeah, I think so too.
We've got these calculations going on.
Yeah.
It's using some pretty complex math,
Mm-hmm.
something called numerical methods.
Yeah, numerical methods. Those are really important.
Yeah, to get those pH changes super accurate. Yeah, and one of the methods that it uses is the bisection method.
Bisection method.
Yeah.
Numerical methods.
Yeah, it's pretty cool, actually.
I feel like a little intimidated.
Oh, no. It's not as scary as it sounds.
Okay.
So the bisection method is kind of like a guessing game.
Okay.
So imagine you're trying to find a specific page in a big, thick book.
Okay.
You know it's in there somewhere.
Right.
You open it up halfway.
Yep.
Is the page you want before or after.
Uh-huh.
You eliminate half, and then you do it again and again.
Right, narrow it down.
And you narrow it down until you find the page you want.
I see.
The bisection method does something similar,
Okay.
but with math equations.
All right.
And it keeps having those solutions until it finds the exact one.
It's like a super efficient way to find the answer.
Yeah.
So the simulation's using this for those pH changes.
Exactly.
Okay, now that's impressive.
Yeah.
But even this simulation's got to have limits, right?
Of course. Every model has its limits. This one's for monoprotic acids
Okay.
and monofunctional strong bases.
Okay.
But the developers actually suggest ways to expand the code to include weak bases.
Oh, wow.
And even acids and bases that can give up or take more protons.
So it's like a foundation
Yeah.
we can build on.
Right.
I like that.
Mm-hmm.
Now, speaking of pushing the boundaries,
Yeah.
the developers included some thought-provoking questions in the material.
Oh, that's great.
It's like they want us to think critically about what's going on.
Oh, I love that.
So I think we should take a look at those.
Yeah, let's do it.
But before we do, I want to challenge our listeners to think about these questions too.
Okay, sounds good.
All right, so here's the first one. Does the volume of acid we start with, VA, actually affect the results? Think about that one for a second.
Okay.
And there's another one. What if we switched out the base? What if we used potassium hydroxide, KOH, instead of sodium hydroxide?
Interesting.
Would that make a difference in our titration? And finally, Can the pH of a solution ever go outside the 014 range?
That's a good one.
Take a minute with that one.
Right.
That might challenge what you thought you knew about pH.
Definitely.
So we're going to dive into those answers in a bit, but first we're going to take a quick pause.
Okay.
Gather our thoughts.
Sounds good.
Don't go anywhere. Things are about to get even more interesting.
I can't wait.
Okay, I hope you've had some time to think about those questions, because now it's time for the big reveal.
Let's do it.
Let's start with the volume of acid,
Okay.
VA.
Mm-hmm.
Initially, I thought, of course it matters.
Right.
More acid, more base needed, right?
Yeah.
But then I started thinking about the calculations involved.
Right, so it's easy to get caught up in that.
Yeah.
But remember, we're ultimately interested in that concentration.
Mm-hmm.
And this simulation does all those calculations for us.
So even if we have like a swimming pool full of acid,
Yeah.
the simulation can still pinpoint that concentration.
Exactly.
Wow, okay.
It takes all the guesswork out of it.
Yeah.
You don't have to do those tedious calculations by hand anymore.
That's awesome.
Yeah.
Okay, what about switching up the base?
Okay.
Does it matter if we use sodium hydroxide or potassium hydroxide?
That's a great question.
I remember learning about different types of bases, but I don't really remember the specifics.
Sure, so as long as we're dealing with a strong base,
Okay.
like sodium hydroxide or potassium hydroxide, it actually doesn't matter.
Wait a minute. I'm a little skeptical here. I mean, sodium and potassium are different elements, right?
Right, they are.
How can they have the same effect?
Well, the key here is that when a strong base dissolves in water, it completely breaks apart.
Right.
And what really matters is that hydroxide ion.
Okay, the OH.
So it's the hydroxide ion that's neutralizing the acid.
Exactly. It reacts with those hydrogen ions from the acid to form water.
So sodium and potassium are just kind of hanging out?
Yeah, they're just spectators.
I like that.
Okay, now for the mind-bending question.
All right.
Can pH go outside the 014 range?
It can.
Really?
Yeah.
I always thought that was like the limit.
Yeah, it's a common misconception,
Okay.
but in extreme cases, it can definitely go below 0 or above 14.
What kind of scenarios would cause that?
So think really concentrated acids
Okay.
or bases, like concentrated hydrochloric acid.
Yeah.
That has a pH well below 0.
Okay.
And then on the other end, you have a concentrated solution of sodium hydroxide.
Yeah.
And that can have a pH above 14.
So 0 and 14 are more like guidelines?
Yeah. I guess you could say that.
Okay, I'm starting to feel like I need to go back to chemistry class.
Oh, no.
But this is fascinating stuff.
It is. It's really cool.
It's really cool.
Yeah.
And this JavaScript model is just amazing.
I know. It lets us explore all these things without actually having to use dangerous chemicals.
That's like a virtual playground.
Yeah, exactly.
But, you know, it's not just about playing around. There's real educational value here.
Absolutely.
So I think we should talk about why this matters for our listeners.
Yeah, definitely.
I mean, you know, why should they care about all of this?
Well, imagine trying to learn about titration from a textbook.
Yeah.
It's all words and diagrams.
Right. Very abstract.
It's hard to picture what's actually happening.
Exactly.
And that's where a simulation like this is so valuable.
Yeah.
It makes those concepts visual. It's interactive.
Yeah, you can actually see those pH changes.
Exactly. And you can tweak things and see how it all connects.
Like having X-ray vision into the reaction.
Exactly.
And it encourages experimentation, too.
Absolutely. You can change the concentration, the volume, try different indicators.
Yeah, you're in control. And you can see how each change impacts what happens. It's really amazing.
Yeah, it's really cool.
And it also highlights the role of math in science.
Yes. It shows how we can use math to represent and predict real-world phenomena.
It connects those equations in the textbook to what's happening in a beaker.
Exactly.
I like that. And you know what else is exciting?
What's that?
The developers suggest ways to expand the code.
Oh, yeah, I love that.
So even this model can be improved and refined.
Right. Science is always evolving.
Exactly. Always pushing the boundaries.
Yep.
Well, I think we've successfully titrated our way through this discussion.
I think so, too.
But before we reach the equivalence point of this deep dive, I want to leave our listeners with a final thought to ponder.
Ooh, I like a good cliffhanger.
We've talked a lot about monoprotic acids and strong bases, but what about all those weak acids and bases out there?
Right.
How would their titration curves look different?
That's a good question.
And how could we modify this simulation to represent those reactions accurately?
That's a challenge for our listeners.
Yeah, a puzzle to solve.
Exactly.
You know, if you're out there and you're feeling a little lost,
Yeah.
remember that tools like this simulation are here to help us.
They really are. They can show us the way.
You know, this is just one example of how Simulations are changing the way we learn about science.
Yeah.
Imagine trying to teach this stuff even 10 years ago.
I know. It's crazy to think about.
We would have been stuck with, like, diagrams on a chalkboard.
Yeah, and equations.
Yeah.
No way to really see it happening.
It's like we've gone from black and white to HD color.
That's a great analogy.
And what I really love about these simulations
Yeah.
is that they make learning active.
Right. You're not just sitting there listening.
Yeah, you're not just memorizing facts.
We're actually doing something.
You're experimenting.
Exactly.
You're testing things out.
And discovering stuff for yourself.
That's what real science is all about, right?
Absolutely.
It's not just about knowing the answers.
Yeah.
It's about asking the right questions.
I think those questions from the developers were really good.
Me too.
They make you think about the bigger picture.
Yeah, they do. And that's what I really want our listeners to take away from this.
Okay.
Don't be afraid to dig deeper. Question things.
Yeah.
And keep learning.
Always be learning.
Now, we've been talking about this one specific simulation.
Yeah.
But remember, science is huge.
It's massive.
This is just one tiny part of it.
a small piece of the puzzle.
But it's such a fascinating piece.
It really is.
It gives us a glimpse into how chemistry works.
Yeah.
All the intricacies of it.
And it makes you wonder what else is out there.
Exactly. So keep exploring, keep learning, and keep that curiosity alive.
That's what it's all about.
This has been a great deep dive.
It has been.
I hope you've enjoyed it as much as we have.
Me too.
We've learned about titrations, numerical methods.
Yeah. And the amazing world of pH.
But most importantly,
Yeah.
I think we've shown that science can be exciting.
It can be.
It can be engaging.
Definitely.
And it's for everyone.
Absolutely.
So go out there and explore the world of science.
There's so much to discover.
And until next time, happy learning.